Equatorial Africa. A huge river flows across a vast stretch of savanna and tropical rainforests. The Republic of Zaire lies on both sides of this river. People here will soon see a gigantic suspension bridge, constructed for the first time in Africa. The Republic of Zaire lies in the central part of the African continent, spreading on both sides of the equator over a space area of about 2,340,000 square kilometers. But its coastal lines extend only 30 kilometers on the Atlantic side, with its inland area spreading far inside the continent. In terms of land space, Zaire is one of the largest countries in Africa. Through the colonial times, as the Belgian Congo, this country became independent in 1960 and in 1971 was renamed as the Republic of Zaire. The whole nation today are exerting themselves to achieve economic independence and modernization all by themselves. Kinshasa, the capital and the largest city of the country, holds nearly 10% of the national population of about 26 million. However, traffic and transport systems are not well organized yet. Transport of mineral resources yielded in the central and southeastern areas is done by means of its railways operated on a modest scale and boats navigating up and down the Zaire River and its tributaries. The port of Matadi, about 150 kilometers upstream of the Zaire River from the Atlantic Ocean, functions as the country's trade center, but considerable amounts of losses are inevitable in terms of time consumed and economy, so long as the goods in transport are transferred from the railways to the ship or the other way round. In fact, nearly all of the mineral products accounting for most of the earnings in foreign currency are shipped for export through the neighboring countries. With the aim of exporting their own products out of their own country, the government drew out a railway construction plan, which might be called the National Front Project, involving the construction of a port in Banana. The main part of the project was to construct a bridge in Matadi spanning the Zaire River. This project was launched in 1971 when President Mobutu of the Republic of Zaire visited Japan. His visit resulted in the immediate implementation of the project with overall economic and technical cooperation of Japan. The Japanese government dispatched bridge construction experts to the Oebk, l'Organisation pour l'équipement de Banana-Kinshasa, which is under the direct control of the Zaire government. A Japanese consortium won the order for bridge construction. This consortium consists of Ishikawajima Harima Heavy Industries Limited, Mitsubishi Heavy Industries Limited, and Kawasaki Heavy Industries Limited. The consortium took charge of everything: investigation and designs of the overall construction work, the construction of substructures, the fabrication and installation of the superstructures, roadway construction, etc. The new bridge is to be a suspension type for combined use of railways and roadways. In coping with the demanding tasks for specific and highly sophisticated bridge construction techniques, a technical committee was organized, consisting of leading figures in the Japanese bridge construction engineering, who provided technical advice. To construct a suspension bridge incorporating the best of bridge construction technology, the consortium made continuous studies and repeated discussions on various aspects involving surveys and investigations, designs, construction, etc. The bridge should be a 3-span continuous truss stiffened suspension bridge without suspending the side spans, with the central span measuring 520 meters and the side span 91 meters, to make up the total length of 722 meters. The upper surface of the stiffening truss used for the roadway and the lower surface for the railway. The structure is carefully designed for economy and shortening of the work period, such as the composition of the main truss and the steel deck. In the fabrication and installation, several investigations and tests were conducted to clarify characteristics about aerodynamic stability and conditions of train running. A wind tunnel test is one of the examples. Studies on aerodynamic stability and the train running conditions help us confirm the appropriateness of the type of suspension bridge and the basic design. The technological achievement involving this bridge, designed for combined use for the railway and roadway, will provide us worldwide with invaluable data for tomorrow's bridge construction technology. This is the construction site of the bridge viewed from the city of Matadi in the year the work was started. Here, attracting our attention, is the narrowest part of the river, where steep cliff-like hills fall, so to speak, down to the riversides. Now we begin with detailed studies of geology. Based on the studies made, the designing of the bridge and the foundations and the access road proceeds with increasingly clear-cut details. Excavation has started around the hill where the anchorages are to be constructed. Here, seen under the weathered layer of earth, is a hard rock bed to support the bridge. This is the Precambrian rock layer, considered to be 500 million years old. The anchorages have been designed basically to be a gravity-type direct foundation structure, supported by this hard rock bed. A couple of foundations in each pier with an 8-meter diameter are to be constructed by means of the deep foundation method. The loading test of the supporting rock bed. The test helps us to confirm that the hard earth layers have sufficient strength as a supporting ground for the huge suspension bridge. Pouring for pier foundations is proceeding as planned. A large number of Zaire people have been employed to deal with the substructure construction, providing significant labor force. Aggregates for concrete were quarried in the rocky hills nearby, and batcher plants built at the work site to ensure stable supply of massive concrete. While the substructure work was progressing, reclamation work for the access road went on smoothly by excavating part of the hill. In the highlight of the substructure construction, President Mobutu visited the work site. Standing in the middle of the bridge construction site, the President observed the progress of the construction work. The entire nation is anxiously awaiting the completion of the bridge with great expectation. In Japan, the fabrication of bridge superstructures was proceeding smoothly. The three companies in the consortium have the most up-to-date specialized works for the manufacture of large steel structures, as well as capable engineers and skilled workers who rank among the world's best. In the trial assembly of the main tower, the metal touching of the blocks proved far better than 90% of tightness rate. Precise facing of the tower base bottom plate surface is followed by machining each end of the truss members. The adoption of high tensile steel for this bridge requires particularly stringent quality control in welding. For that reason, tests for execution of welding were carried out to find out the best way of welding method, which then was applied to the actual welding. Each factory keeps assembly precision of structure members under rigorous quality control, taking advantage of their accumulated know-how in bridge construction. This is a three-dimensional trial truss assembly incorporating the steel deck. The anchor frames are also assembled temporarily in full scale for erection. Assembly precision is pursued to the extreme until the slightest of error has been corrected. The bridge structure members, just completed by the three-company consortium, are now being shipped to Africa. It's about 20,000 kilometers from Japan to the African port city, sailing through the Malacca Straits, then across the Indian Ocean, and round the Cape of Good Hope into the Atlantic Ocean. It's about a month since the freighter left Japan. Now it has sailed along the Zaire River, passing by the bridge construction site to arrive at the Matadi port. A number of heavy machines and structure members are unloaded one by one. Temporary facilities to be installed at the work site, machinery and bridge members, including superstructure components, are all transported from Japan. The erection of the superstructure has just begun. The anchor frames for cable fixing are assembled into the concrete anchorages. Here, the main tower is erected. For an economical reason, the main tower is 11 partitioned in the height direction with a cross-sectional structure consisting of 4 panels. The adoption of the lift-up crane method, newly devised for the tower erection, is a new departure from the conventional method. In this method, the crane placed on the tower deep beam, finally installed as the tower top horizontal beam, helps to erect the main tower each time after winding up the beam with a winch. This minimizes or reduces installing facilities, resulting in contribution to the economy and stability of the bridge construction, an excellent method indeed. In this way, the main tower can be erected firmly high above the ground. Two years after the construction start, the construction work has progressed to the state of erection of cables, linking the 2 towers and the anchorages on both banks in the air scaffoldings called catwalks are prepared crossing high above the Zaire River. The erection of cables begins with the stretching and spanning of a pilot rope. To prevent the rope from being caught by the swift current, it is drawn out by a tugboat which keeps it hung in the air. Then a temporary hauling rope is stretched, making use of the pilot rope just installed. This is followed by the erection of the catwalk, which is stabilized with storm ropes, and then the hauling ropes are fixed. Individual parallel wire strands are pulled out one by one above the catwalk, and then are finished into a round cable with a diameter of 480 millimeters. At the central span, hanger ropes are suspended, and erection stiffening trusses follow. A single strand of the cable consists of 127 wires bundled together, each having a diameter of 5.15 millimeters. The erection of cables is the highlight of suspension bridge construction. Every care has been taken and exercised before the actual construction at the site, using full-scale models for installation tests in Japan. After the strands have been made into a desired shape above the catwalk, it is transferred to the saddle. The pulling of strands is individually repeated 56 times on either side of the bridge. The locations installing strands are simultaneously shown on the indicator panel set at the construction site base. Under thoroughgoing control, the strands are pulled across the tower top over the river down to the anchor frame where the cables are to be attached. Sag adjustment is carried out during the night when temperature changes are usually decreased. Each sag is adjusted conforming to the standard strand. The strand, which has been drawn to the anchor frames, is now firmly fixed. In this way, the installation work of the cables, the lifeline of a suspension bridge, proceeds to its final stage. Now cable bands are clamped around the cable, which has been completed in round shape. After this, hanger ropes are hung down at the central span prior to the attachment of stiffening trusses. Meanwhile, the anchorages where the cables are attached are ready for concrete pouring. In the substructure construction, mass pouring of concrete has been carried out using about 25,000 cubic meters per anchorage. When huge amounts of concrete are poured at one time, considerable heat is usually produced, providing a possibility of making cracks in the concrete. To prevent this, concrete pouring has gradually been done, dividing into 105 separate blocks. The Boma side road makes a sharp turn to the right, where the bridge foundation is to be constructed, and requires excavation of a steep slope, a job attended with a great deal of engineering difficulties. The work, however, is rapidly proceeding. Under the cables, the erection of stiffening trusses has started. The side span trusses have been completed by the bent-used method. The top chord, bottom chord, and diagonal structure members are all installed member by member, fastened with torque shear type high-strength bolts. Underway parallel to the side span erection is the erection of tower links, which function as intermediate supports of the stiffening trusses. The construction work will soon be faced with the rainy season. Fortunately, however, the work has hardly been hampered by the unfavorable weather. The design with due consideration made on erection. It has been drawn out to let the superstructure and the substructure works progress in parallel. Machines and equipment, as well as personnel arrangement, have been effectively made. In addition, the work period has successfully been shortened by more than a year, thanks to the enthusiastic cooperation of people in Zaire who have long wished for the completion of the bridge. Prior to the stiffening truss closing work, one of the members of the technical committee make an inspection at the site. Now the last stiffening truss member is fitted in, finally linking up both banks. First, the bottom chord is firmly connected. top cord is placed in position with great accuracy. People now wait for the dramatic moment of closing work on the final stage, each reminiscent of the memorable scenes of the work he has been responsible for. Finally, the steel deck is set in position, filling the space above the river. The completion of carefully planned operations for bridge construction. The superior technical capabilities of the three-company consortium, and the devoted endeavors exerted by the Zaire employees. With all these put together, the bridge spanning this magnificent river, the Zaire, will soon be completed, symbolizing the efforts of all concerned. The work still continues towards the finish. Cable wrapping. The cable with a 480 millimeter diameter is being shaped into complete form. For protective treatment, only the finishing coat is done at the construction site. Here, the employed Zaire people are having technical training led by Japanese engineers. Steadily underway here is the paving work of the access roadway that extends in total 8 kilometers on both sides of the river. A loading test is conducted from midnight towards dawn, when the operation and the test results are least affected by temperature changes. Now the bridge is going to hold a maximum load of 750 tons. The loading test has resulted in the confirmation that the design has been correct and the work execution excellent. Here, the huge suspension bridge spans the Zaire River, demonstrating the advanced technology of bridge construction. The city of Matadi, seen behind the river. Traffic between both sides here accounts for 10,000 people and 300 cars per day, carried only by this ferry boat, which plies several times a day between both banks, struggling its way through the rapid stream. We need a bridge here. It's been a long, cherished wish of people in Zaire. And their wish will soon be answered. The 21st of May, 1983. The opening ceremony was delightfully held, inviting President Mobutu.
Matadi 橋の完成により、ザイール経済の発展とザイール国民の生活の向上に大きく貢献するに至ることを願ってやみません。
The construction of the Matadi Bridge, a contract for a 64-month work period, has been finished in only 50 months, a year and 2 months shorter than the signed contract period. helping their national construction project take a large stride forwards, as well as meeting their great expectations. The new bridge is filled with lots and lots of people who have come to celebrate its completion. Our bridge-building technology has brought about memorable achievements in Africa in the form of a gigantic suspension bridge spanning this impressive river, the Zaire.